So just like the way we have seen the examples in 2D, right? We have seen these examples in 2D. Let's see the examples in 3D. Here for the 2D examples, if you notice, when we started off, we said that your W is a scalar, right? We said W is a one-dimensional scalar. Imagine if W is two-dimensional. Let's assume W is a two-dimensional vector. In a deep learning case, your W is many dimensions because you have tons of weights, right? You have lots of weights. Your WKIJ has thousands and thousands of weights. But let's try to understand just the way we have understood when W is 1D, we have understood this. What happens in 2D? Because we can visualize up to 3D, right? We can't visualize any further. So here what happens is, now let's assume my W vector has two dimensions, W1 and W2, right? This is my W1, this axis is my W1, this axis is my W2, and the z-axis, so let's call this x-axis, this is my y-axis, and this is my z-axis, right? My z-axis here is my loss, right? Because your loss, remember, because your loss is a function of W, and W itself is a vector. W itself is a vector. So your loss will change if either W1 changes or W2 changes, right? This is basically going from scalar to vectors, right? So here I have my weight 1, here I have my weight 2, and my z-axis here is the loss. And what you see here is a convex. This is a convex one. This is a convex loss function. This is a generalization of hyperbola. This is a generalization of parabola. This, what we see here in a 2D plot, the same thing we are seeing this in a 3D plot, right? Very interesting, very simple actually, right? This is also convex because if I take a point which is there in this region, so here just the way we painted these regions, in 3D also I can paint everything above this curve is one region, everything below this curve is another region. Right? Just look at my pointer. Everything above this curve, everything which is inside this curve is one. Everything that is outside this curve is another region. Suppose if I want to go from this point to this point, of course, all the points that I touch are within this region, and hence it is convex. Number one. So this is an example of a convex loss function when your weights are two-dimensional, right? And your loss function is plotted on the z-axis. Number one. Number two. You notice these lines here? Those are called contour lines. Those are called the contour lines. And what they mean is this. So let's take this line. Let's take one line as an example. This line basically says, so here, what I do here is this. The way I plot these contour lines is very interesting. I take all the points that are at the same height. So let's call this length. Let's call this width, and let's call this height. Okay, easy for us to visualize that way. So you take all the points that are at the same height. Okay, suppose this point, all these points are at the same height. You take all the points that are at the same height. Okay, and you can now, because visualizing in 3D is hard, right? Because you can't plot 3D on a 2D paper. It's hard because I can't rotate this. I need a computer and all of that stuff, right? So what people have done is people have tried to visualize your 3D functions in 2D. Okay, people have tried to visualize this because this is a 2D surface, right? This is a 2D surface. This surface that I have here, this surface I have is a 2D surface. So they've used contour plots. They have used contour plots as a way to visualize your 3D function just using a 2D plot. And the way to do it is, all the points which are at the same height, connect them and draw one whatever shape you get. In this case, you get ellipses. Okay, so this whole ellipse basically says that all these points, so when your W1 is equal to this and W2 equals to this, when your W1 equals to this, W2 equals to this, all these points have the same height or the same loss, right? This plot, this bottom plot that you get is called a contour plot. Okay, let me show you another contour plot. And by the way, I'm just getting this by doing a simple Google search, right? I just simply Google searched for convex 3D function and I got this plot. Nothing rocket science there. Very, very simple. You get lots of functions and I picked the one that looked best in my case, right? So let me show you some contours. Okay, contour plot. Just Google image search for contour plot, and this is how a contour plot looks like, right? So whatever is there in 3D, now I'm looking at it only in 2D. Because now what this circle tells me is, okay, that all these points, whenever this, let's say this is W1 and this is W2, whenever W1 is this and W2 is this, all these points have the same height. So this is another way of visualizing 3D data on a 2D surface, right? So look at this. This is a slightly more complex contour plot. What it says here is all these points have the same height. Suppose this is my weight 1 and this is my weight 2. All these points have the same height. Similarly, all these points have the same height. Okay, it takes a while to understand contour plots. Okay, it's not so straightforward. You need some practice thinking about contour plots to understand them completely, right? But let's go. Let's take a slightly complex example, right? This example has multiple minima. Like this is a minima. There is also a lower. There is also descent here. Okay, so there is also a descent like this. There is a minima here. There is a minima somewhere out there within this hole, right? There is one maxima here. There is a maxima here. There is a maxima here. This is a non-convex. This is a non-convex function. Again, if you take this as your weight 1, if you take this as your weight 2, if you take this as your loss, right? This is equivalent to this example. This example where you have multiple minima and multiple maxima. This is a 3D generalization to this 2D plot that we saw in the previous video, right? And this is a non-convex function. And look at it. Look at the contours. For a non-convex function, you have one minima here, you have one minima here, you have one minima here. And a simple way to understand minima is when you have a contour plot like this, right? When you have a contour plot, okay, I don't even have to draw. When you have contour plots like this, okay, I can quickly say that yes, here is the minima. This is the minima. Okay, this is my, let's say, W1, this is my W2, this is my minima. For a non-convex function, you'll see a lot of these stuff. When I see this, I know this is a minima. When I see this, I know this is a minima. When I see this structure, I know this is a minima. And when I see this structure, I know there's a minima there, right? So for the complex case that we saw here, let's take this case that we saw a while ago, right? Let me just click on this. Okay, for this case, I can quickly know that, okay, there is a local minima here. There is certainly a local minima here. There is a local minima here. There is a local minima here, and there could be a local minima there also. Okay, so by just looking at a contour plot, I can understand where the local minima are. Like for example, if I take this other example, right? And all these are readily available on Google image search, right? So if I see this, I know, okay, there is a local minima here and there is a local minima here. And the coloring can tell me whether, see, this is a deeper red, right? This region is deeper red, which means that this is also a global minima. So sometimes you get color coding, sometimes you don't get color coding. For example, in these plots, you don't get color coding. Sometimes you get color coding. Sometimes in contour plots, you also get this very nice visualization. Let me just get this. Sometimes people also say, all the points which are here, right? What is their y? What is their z value? Right? This is my W1, this is my W2, and this is the z value, right? They also say that the z value here is 1.5. The z value here is 1.2. The z value for all these points is 0.9. So you also get some color coding or numbering in some cases of contour plots, right? So we have seen simple convex 3D function, non-convex function. We have seen, let's look at saddle point now. This is a Wikipedia article, right? The saddle point looks like this. The saddle point looks like this. If you look at the saddle point, okay, let me draw it here. It looks like this. So you have, this is a minima here. If you look at it from these two, from this axis, if you look at it from this axis, and if you look at this curve, this is a minima. If you look at it from this axis, right, you get a plot like that, right, going down, right? So you get a maxima here. So at a saddle point, what happens is, at a saddle point like this, what happens here is, because you have this curve coming like this and this curve becoming like this, you have these two curves intersecting here, right? So here your gradient becomes 0, just like in our 2D case. This is just a 3D generalization of the saddle point, and this is called a saddle point because this looks like a horse saddle. Let me show you an example. This is how a horse saddle looks like, right? This is a horse saddle on which people sit. This also has the shape. If you look at it, if you look at a horse saddle, it has this shape where it is like this, and so it's a minima if you look at this surface. If you look at the other side, If you look at it this way, from this side, if you look at it, from this side, if you look at it, right, you get a maxima here. That's why this is called the saddle point, because it looks like a horse saddle. And oh, this is a better thing. The contour plot for saddle point looks like this. Okay, if I actually get the contours, so you get basically you get straight lines here. Whenever you see two intersecting straight lines, so if you see a plot like this, where you have two intersecting lines, and if you see this, if you see a structure like this, okay, let's assume this is W1 and this is W2. And if you see a counter plot like this, I can quickly say that here is a saddle point. It's not a minima, it's a saddle point. Because at saddle point, the contours look like this. So by just looking at contour plot, you can say whether you're at a saddle point, minima, or maxima. That's the fun part about contour lines. And we'll use contour lines a lot in optimization to understand these things better, right? So we have seen, and of course, saddle points can also occur in slightly more complex ways. This is a simple saddle point. Here you have two mountains, right? You have a mountain here and you have a mountain here. Between these two mountains, you have a saddle point here, right? So saddle points can also occur. So this is like the hill climbing analogy that I was talking about. So suppose you're here, you're trying to come down a hill, right? So you might come down a hill and say that, okay, this is minimum, but it's not, because the minima is somewhere here, right? So you could get stuck here without being able to move either in this direction or in this direction. Of course, there are ways to solve it. So simple SGD, simple mini batch SGD, our simple mini batch SGD will get stuck at saddle points, both in 2D case, 3D case, or ND case. So we have seen why it gets stuck in 2D and 3D. The same thing happens even in n-dimensional cases. The 2D and 3D cases are only so that we can visualize it and get a better sense of what's happening. Right? And contour plots, again, oh, this is a nice example of a saddle point in 2D, right? If you have x as this, if this is your x, if your y is equals to x cube, this is your x cube function, right? So this red line that you see is the x cube function. For x cube function, if you look at this, here you have a saddle point because the slope here is 0. But it is neither the maxima nor the minima, right? So you can have a very good example of saddle point in a simple single dimensional case is the function f of x equals to x cube. This had a saddle point at x equals to 0. It's a very, very nice, simple example to understand saddle points. Because the slope here is 0. Because if you draw the tangent here, the tangent is like this with a slope of 0. But it is neither the minima nor the maxima. Right? So this Wikipedia article is very, very interesting with lots of nice examples in here.